And in today's video, we're gonna go over the life cycle of a star. Wow, I am branching off into different subjects now. Astronomy. Where am I gonna go next? Should I go to business next? Did I go to drawing? Then I don't know. The options are limitless. Okay, so we're just gonna talk about stars today. Pretty cool. Pretty cool. Okay. So we're gonna learn about molecular clouds, nuclear fusion, supernovas. Oh, I used to be interested in being a space scientist, but not for me anymore. But our central theme is a star's entire life cycle, its duration, its final fate, and the elements it produces is determined strictly by a single variable: initial mass. Oh. Okay. Uh, Also, Jerry did a new theme today because we're talking about stars, so he made it galaxy themed. Oh, wow. Ho ho. Look at this picture. You know when we take pictures of space, we don't actually space is actually colorless. Well, not colorless, but not these vibrant colors. So when we take those pictures, like with the Hubble Space Telescope, we have to add in the colors ourselves. That's an interesting thing. But okay, so a nebula, the stellar nursery. So stars begin in a cold, dense cloud of gas and dust called the giant molecular cloud or nebula, and then gravity pulls material inwards. As the cloud collapses, it fragments into smaller clumps, and then friction and compression raises the temperature, forming a protostar. And then the conversion of angular momentum causes the cloud to spin and flatten into a disk. Next, we can talk about nuclear fusion, which is the engine, which once the core of a star reaches 10 million Kelvin, nuclear fission can begin. This marks the transition from protostar to main sequence star. Here's the equation here. And then the mass deflect or lost mass is converted into pure energy according to E equals mc squared. You can see here, nuclear fusion, that's how we make energy on Earth as well. So, yeah. Okay. Next, there was supposed to be a diagram, but Jerry isn't. I don't know. He's probably in Fiji right now. I'm not gonna lie. But we can talk about hydrostatic equilibrium, and that's where a star is a battleground between two opposing forces. For a star to be stable, these forces must be perfectly balanced. The first force is gravity, which is pulling the star's mass inward towards the core, and then we have radiation pressure, which generated by fusion pushes upwards. And then when these forces are in balance, the star is in equilibrium. Oh, the diagram is actually there. Okay, now we can talk about the HR diagram, which is the Hertzsprung-Russell diagram, which is the periodic table of stars. And it plots stars based on two variables: luminosity, the total energy output, and the surface temperature, which is spectral class. And 90% of stars fall on the main sequence, where they spend most of their lives burning hydrogen. You can pause the video now to look at this graph. Just understand it. Try to understand it yourself. Okay, we can move on now. So we can talk about the lifespan versus mass of a star. So counterintuitively, the more mass the star has, the shorter its lifespan actually is, because it consumes fuel at an exponentially faster rate. And looking at a blue giant, which is the O-type, the solar mass is around 20 to 60, and the surface temperature is 30,000 Kelvin more, and then the lifespan is approximately 10 million years. Now you might think that's a long time, but but compared to other stars, that's a very short amount of time. Like looking at the sunlight, which is the G-type, which is 0.8 to 1.2 solar masses, which is around 6,000 Kelvin, it can actually live to 10 billion years. And then if we look at red dwarfs, the M type, at 0.1 to 0.5 solar masses, it is around 3,000 Kelvin, but it can actually live to over 100 billion years old. That's a long time. That's a very long time. I don't think I can even count to that long. hmm. Oh, oh, uh, sorry, I was looking at my text messages. Okay, so we can look at a red dwarf. Look at this red dwarf. It looks like our sun. But when hydrogen in the core is depleted, this is post MS, by the way, fusion stops and gravity wins and it crushes the core until it's hot enough to fuse with helium. And the core contracts and heats up, and the outer shell of hydrogen expands and cools. The star becomes a red giant. So our sun will enter this phase in roughly 5 billion years, expanding to the orbit of the sun. I meant the Earth. So that means we can touch the sun. I don't know if that's a good thing. I'm not gonna lie. Where are we gonna be in 5 billion years? Something like that. Well, we all have our things, but he is our son. Pretty cool. But he is the. What the? Oh, now I think I know why Jerry puts this. I think when the picture isn't able to get uploaded, that's the size of the image, so 600 by 400 pixels. Oh, that makes sense. Okay, so death of low mass stars. So first is a planetary nebula, and that's when the low mass stars cannot fuse elements heavier than carbon, and they eject the outer layer into space as a glowing shell. It's pretty pretty. That's so pretty. But the second one is a white dwarf, and there would be a white dwarf picture, but Jerry. Okay, so the leftover core is about the size of Earth, but the mass of the sun. It is supported by electrodegeneracy pressure. Wow. And then we have high mass supergiants. Look at this. This is beautiful. But stars more than 8 times the mass of the sun go through a much more violent evolution. They can fuse heavier and heavier elements in the core. And as each fuel runs out, the core collapses further and further, starting fusion for the next element. This creates an onion skin structure. So the element produced goes from carbon to neon to oxygen to silicon to iron. But then when it reaches iron, that's when it reaches a dead end. Why? It's because iron is the most stable nucleus. Fusing iron consumes energy rather than releasing it. And then when iron forms in the core, the star's energy source almost basically vanishes instantly. And then the core collapses, since without radiation pressure, the gravity wins permanently. And then the core collapses in the fraction of a second, reaching a quarter of the speed of light. And then we have a supernova type 2. It's beautiful. Oh my. A single supernova can briefly outshine the entire galaxy of 100 billion stars. It's pretty bright. But when I stand to my light, that's pretty bright, too. So, like, I don't know how that can be more brighter. But explosive nucleosynthesis. The shockwave from the collapsed core creates all elements heavier than iron, like gold, silver, and lead. Every heavy element on Earth was born in a supernova. Wow. Oh, I skipped neutron. So neutron stars and pulsars. If the remaining core is about between 1.4 and 3 solar masses, it becomes a neutron star. And it's entirely made up of neutrons. Density of 1 teaspoon weighs 1 billion tons. I can bench that. And then pulsars rapidly spinning neutron stars that emit radio beams, roughly the diameter of a large city, 10 to 20 miles. You can look at this. It's a pretty cool picture too. The black holes. Look at that. I don't know why he put this diagram faded in the background, but that's actually pretty cool. I'm not gonna lie. I like how Jeff is designing these slides. But black holes. If the core remnant is greater than 3 solar masses, not even neutron degeneracy can stop the collapse. Gravity crushes the core into a singularity, and um, and that will create a black hole. And I'm pretty sure if you shrink the Earth, like shrink it down to a grape or a golf ball, then that would create a black hole. It's between those two, but I forgot which one. And just one fact about black holes, because why there's no light. The event horizon is the point of no return, and within this boundary, the escape velocity exceeds the speed of light. That's why there's no light coming out of the event horizon, what I'm pointing to right here. That's why it's called a black hole. Okay, so a summary of everything is at low mass, the sequence goes from nebula, main sequence, red giant, planetary, nebula, and then white dwarf. But if it has high mass, it goes from nebula, main sequence, supergiant, supernova, then neutron star. But if it has a very high mass, it goes from nebula, main sequence, supergiant, supernova, then black hole. And a pretty cool quote is, "We are all made of star stuff," by Carl Sagan. And here are the image sources I have. Yeah. Well, I hope you learned something cool. And, if you're gonna go into space astronomy or go work at NASA in the future, please give me an internship. Just reach out to me. I'll take anything. But I hope you learned something cool today, and I will see you in a new video. Bye.